All right, I will begin with a word of prayer. Ahem. Dear Father, we thank you for the weekend just completed and for just another day where we can enjoy your creation and enjoy math. Just help us to glorify you in what we do this day, Lord. In your name I pray. Lord Jesus, amen. So I guess we should top hat, lest the sky fall, right? Let's see here. Like you guys would be like, if I didn't top hat today, you wouldn't even know what to do with yourself, right? I know I would be lost. I'd be like, I just don't even know what to do. All right, let's see here if I can find it. $76.56. 76.56. Yep. The join code is 85306. Oh, I know what it is. So like before the semester started, I like synced the roster to Canvas roster. So a lot of you never put that in, right? Because you were like automatically enrolled. So this is what has been disconcerting about people who added late asking me for this code. I'm like, what code? But I see that there's a code, right? That worked, right? Okay, cool. Let us talk about interesting things. In other words, anything but top hat. So, any questions about the math? So we are covering this week complex numbers, quadratic equations, completing the square, and all that stuff. And then at the end of the week, we cover how to solve radical equations. Now, if I play my cards right, we'll get to some of those radical equations earlier than Friday, I'm hoping. We'll see how it goes. Start with, I need to talk a little bit about something a little bit more sort of lowbrow, if you will. It's just some applications. So example 1, winner of 500-mile race, all right, driven at constant speed of 140.7875, that's random, miles per hour. All right, and then the question is, what was his time to the nearest 1,000th of an hour? Okay, so this is an application of linear equations. We talked just a little bit last class about linear equations. So what's the formula here to work with? What's the relation between velocity, time, and distance? Do you guys know? So we could go with the velocity is the distance over the time, right? Or you could go with the distance is equal to the velocity times the time, right? But what do we want here? We're given what? We're given the distance is 500 miles, right? Yeah, we're given the velocity, so we want the time is equal to the distance over the velocity. And then we just got to be careful with units, right? So the distance here is 500 miles. And we're dividing by the velocity, which is 140.7875. And then you've got miles over hours, right? That's what miles per hour means. Technically, that's miles over hours, right? And so what happens is the miles cancels the miles, right? And we've got, 500 over 140.7875 hours. And that, if you get your calculator, works out to 3.551. Did anybody try it? It says round to the nearest thousandth. What was the, what happens if you actually divide 500 by 144.7875 anyway? Let's try. Say that again. 3.55 what? 166. Okay, so if we take this number and we round it to the thousandth place, we keep the 1 a 1, right? Because the next number is 4, so we don't round up, right? So there it is. To the nearest thousandth. There you go. So that's example 1. Example 2. We've got $970 invested at 11% simple interest. All right, in 1 year. Then the question is, how much interest is earned? So how do you get the interest? What do you do? Interest is what? Principal times rate times time, right? Interest equals principal times the rate times the time. So the principal was $970. The rate, what was the rate? 11%, right? So did we put 11 there? I wish, right? No, like 0.11, right? And the time is 1 year. So like, for example, if instead of having a year you had 6 months, the time would be 0.5, it would be a half a year, right? And what is that? So what do you get? I get $106.70. So is that how much money that you have at the end of the year? That's just the interest that you earned, right? So you take that, if you wanted to know how much money you had in the bank, right? You add that to 970, you'd have $1,076.70, right? And then the government would take all the money that you earned and you'd still have... Yeah, if you can find 11% interest rate, good. But I mean, if you want to lose 11% of your money, it's pretty easy. You just take it out of your pocket, put it in front of you, leave it there for a year, you lost 11%. Because that's how it's going right now, 11% inflation. I'm sorry, did we say 9%? Let's be honest, it's 11. For the purposes of this example and discussion, let's say it's 11. Who really knows? All I know is that I bought a water filter for my house like 2 years ago, and it was $280. My wife bought it yesterday, it was $310.
What kind of water filter is it?
Reverse osmosis. Yeah. All right, anyway, I digress. Anyway, inflation's real, it's happening. Hey, fun fact, do you know if you have $100 in 2005, it's how much in today's money?
Or like 70.
150. If you could take $100 in 2005 and have a similar amount of money today, same worth, 150. Yeah, you're about right, backwards though.
I was doing the other way.
You're going the other way. That's not far off. Where was I? Oh, yes. One more example here. You have a rectangle. All right, you got this rectangle. And it's got a width of 44 centimeters. And it has a perimeter of 180 centimeters. The question is, what's the rectangle's length? How do you figure that out? 180. I guess my question to you really is, how is the perimeter related to the length and the width for a rectangle like this? What do we got? We got W here, W over here, L over here, right? So we got, I heard 2 times the width plus 2 times the length, right? So if you want to figure out the length, solve that equation for L, right? L is 180 centimeters minus twice the width, which is 44 centimeters, all divided by 2. So that's 180 minus 88, which is 92. 92 divided by 2 is 46 centimeters. So I have just a few of these application problems at the start of your homework too, just to remind you some of our basic applied problems that we like to ask about for linear equations, okay?
So, really
Yeah.
fast, we get a page of stuff for all of our tests, right?
You create a page of stuff.
Yes,
Yes.
And we don't get that for the final or the midterm, though, right?
No, so in fact, yes, there are 3 tests. There's no midterm. I mean, if you want, every test is a midterm. Okay, so there are 3 midterms if you want. But each one of those tests, I allow you to create a page of notes, front and back. And then for the final, you can bring 3 pages.
Oh, okay.
I would encourage you to bring those 3 pages that you already created, since those are already your nice summary of the course. And so you ask me at some point, is there a study guide for this course? Yes, you are making the study guide by making that sheet every day you do homework. That is the study guide. It is your responsibility to create it. All right? Just so you know. You're all good. I'm just come back here. All right, so anyway. Now we got these pesky applications out of our system. Let's talk about complex numbers. What are complex numbers? Okay, so let's just get it out here. So the complex numbers are denoted C. So this is A plus IB. Here A and B are real numbers. And I is the square root of -1. So like the critical feature here is that I squared is equal to -1. Okay. So here's just some terminology. All right. Like so this R is also the real numbers. All right. The set of real numbers. The complex numbers, in contrast, are like pairs of real numbers, essentially. We don't need to know everything about the complex numbers here, but I do want to mention them because they're going to come up as we're solving the quadratic equation. We can't avoid it, right? So let's just clear the air and talk about them for a minute. Every complex number can be defined by talking about its real part and its imaginary part. All right, so like, for example, if I had, say, 3 plus 2i, okay, this is a complex number. The real part is 3. The imaginary part is 2. So if you give me a real part and an imaginary part, then I can give you a complex number. So let's see here. What would you like your name today be?
Lauren.
Lauren, give me a real part.
4.
4, okay. And what would you like your name to be today?
I'm just going to go with Aaron.
Aaron, okay. What would the imaginary part be?
Do I have to put the I with the number?
Just you can give me any number. Almost can't be wrong here. Plus 7i. So there you go. So if you give me the real part, you give me the imaginary part, that uniquely fixes a particular complex number. In this case, 4 plus 7i. All right? So these are not real numbers. For example, if I have 6i, what's the real part of 6i? 0, right? So this is called a pure imaginary. This is called a pure imaginary number. The term imaginary is unfortunate. It's historical, but it's not a good term in the sense that complex numbers, like imaginary part of a complex number, is no more imaginary, than the number 2. It's very much as real in the sense of existence as real numbers. They're not real numbers, so for that reason they're called imaginary, but it's really just an unfortunate term because complex numbers do exist, they're useful, and we can describe many things with them. If you study engineering, electrical engineers use complex numbers to model what's called the impedance of a circuit with AC current, right? You use real and imaginary part to describe how like capacitors and inductors respond to an oscillating current and so forth. There are many, many applications of complex numbers. But this is a pure imaginary one. Here, one more. They have some interesting patterns. What happens if you look at I to the power 10? How does that work? So you get I squared times I squared times I squared times I squared times I squared. 5 of them, right? But I squared is what? -1, right? So we got -1 times -1 times -1 times -1 times -1, also known as -1, yeah. So I to the power 10 is just -1. Almost done with this quick tour of complex numbers here. Here's something interesting. Since I squared is I times I, that's equal to -1, right? What does this mean 1 over I is equal to? Can you see it?
Would it be I to the -1 over the numerator, right?
Well, yeah, but just look up here. What happens if you divide? I mean, this could also give us -I times I is equal to 1, right? So what happens if you divide I to the other side? What do you get? Like, take this equation, divides both sides by I. What happens? So I over I equals 1 over I. So the i's cancel. And we get 1 over I is, in fact, -I. So that to me is a little bit disconcerting, but that's how it works. I mean, there's weird consequences of having I squared equals to -1, right? This is not how real numbers behave. But it is true, every non-zero complex number has like a multiplicative inverse. We don't actually need to get into that for this class, so I won't do it. But I will do this much, because this kind of calculation will come up for us a little bit. What if you had like 3 plus 4i times 2 minus, let's say 7i. How would you calculate this product? In other words, how does complex number arithmetic work? I'll give you the short story of it without even defining it. The answer is you just calculate like normal. You still have the distributive law. Everything's the same. It commutes even. But the weird thing is, of course, that you have to keep track of the fact that I squared is -1. That's pretty much it. So I could distribute. This is like 3 times 2 minus 7i, right? Plus 4i times 2 minus 7i. So I distribute, and then distribute again. All I'm really saying is FOIL, like FOIL it out. So 3 times 2 is 6. 3 times minus 7 is minus 21i. Then we get plus 8i, and then minus 28i squared. And then you want to collect like terms. What is I squared? -1. So this whole term right here is really what? Minus 28 times, it's really plus 28, right? So we get plus 28 plus 6, which is 34. And then we get minus 21 plus 8, which is minus 13, right? Minus 13i. And there you go. And it turns out any two complex numbers you can multiply and you get another complex number just like this. Right? Oh, there's so much more interesting things to tell you here, but I really shouldn't tell them for this class. I mean, interesting things I could tell you would be like, if you calculated the length of this complex number and the length of that complex number, the length of the product of the two numbers is the product of the lengths. And if you could calculate the angle of this complex number and the angle of this complex number, the standard angle of the product would be the sum of the standard angles. There's like beautiful geometry in here. So if you go on and take, if you choose to add the math major, you should add the math major. I mean, you should consider adding the math major if you like math. We can talk a lot more about the structure of the complex numbers in like the complex analysis class, or even in maybe like, I talk about it some in like differential equations sometimes. But anyway, enough complex numbers. This is all we need. All right. So, any questions? I'm not really going too deep. This should be enough for you to do the homework. I think I've talked about the terminology. If there's just the imaginary part, it's pure imaginary. If there's no imaginary part, it's called a real number. Real numbers are particular kinds of complex numbers. Let's see here. Yep.
Are we going to do it like I cubed and I to the fourth, or is it just really going to say with I and I squared?
Well, we had I to the 10th here. We could talk about something else, What would I to the 5th be? So you've got I times I squared, right? What is I squared times I squared? Yeah, it's minus 1 times minus 1, which is, so it's I again. So actually, like a helpful hint, something you can use to simplify those problems in the homework is like I to the 4th is equal to 1. So this, you could use that to simplify. If I asked you, what's I to the 81? You could calculate that real easy, right? Because like I to the 81 would be what? It would be I to the 4th raised to the 20th power times I. So like the 80th power is 4 times 20, right? But I to the 4th is 1, so that's just 1 to the 20 power times I. So you're right, the thing in parentheses is 1, right? But there's a leftover I. Don't poke your eye out. I mean, don't poke the eye out. There's an I. So the answer is I again.
What about I to the third?
I to the 3rd is I squared times I, which is minus 1 times I, which is just minus I. There is one other issue with notation I should talk about, and this is actually pretty relevant to our continuing discussion here. What if you had something like the square root of minus, 64, let's say. So the way this works is you can look at that as the square root of minus 1 times the square root of 64. The square root of minus 1 is I, and the square root of 64 is what? 8. And I just like to write that as 8i, just as a matter of style. Here's another one. Square root of like minus 17 is just equal to the square root of minus 1 times the square root of 17, which we could write as I times the square root of 17. It doesn't take long before you get bored of the middle step, right? And just do like I'm about to do, which is say like square root of minus 137 is equal to I times the square root of 137, like that. So if you got a minus inside the square root, you can promote it to a I times the square root without the minus. Just that. Okay? So here's the thing. If we allow complex numbers in our universe of discussion, when we study quadratic equations and you ask the question, does this quadratic equation have a solution? All right, the answer is yes. If you allow complex answers, there's always a solution to a quadratic equation. However, if you don't allow complex solutions, right, then sometimes there's solutions to quadratic equations and sometimes there's not, right? So let's talk about that. Let's see here. So what is the quadratic equation? So I want to talk to you about how to solve the quadratic equation in a few different ways. All right? And I do need you to understand all of the different ways we're going to do it, because I'm going to ask you to solve it a couple different ways, all right? So it's important you understand what I'm doing as we go forward here, okay? But what is the quadratic equation? It is this: ax squared plus bx plus c equals to 0, right? Where a, b, and c are real numbers, and a is not equal to 0, right? This is the quadratic equation. We'd like to know how to solve these. Sorry if I'm in the glare for you. How many of you, can I shut that? Does it still have the draggy thing, or is this the one I took one of these I may have pulled the thing off of? Was that this class? I didn't damage the window. Does it still have the pulley thing? Oh, okay. See, the other room, the pulley thing is long gone. And so I may or may not have removed one of the blinds in an effort to do this. There. Would you like your whiteboard without a glare? You're welcome. All right, so how do we solve this? Let me go through the general solution. Here's what you do. We divide by a. So divide by a, we have x squared plus b over a times x plus c over a equals to 0. That's step 1. All right? Step 2, I will do what's called complete the square. Completing the square, we take x, we take half of this, b over 2a. I square that. Now, let me talk about this.
Why isn't the bx, why isn't the x and the bx divided by a as well?
Well, I divided bx by a, so it's b over a. I mean, well,
I guess it's the same thing.
yeah, okay. I mean, we have options. You could write it bx over a. You could write it b over a times x. You could write it b times x over a. These are all equivalent.
Okay.
But my point here is that these first two guys, right? If you FOIL this back out, you get back x squared, and you get back b over 2a x, and then another b over 2ax, if you think about multiplying this out, right? So we get back these two terms, but what else do we get? We also get b over 2a times b over 2a. So to be fair, we have to subtract that, otherwise we've changed the expression. So I subtract b squared over 4a squared. Okay? And now with that addition, everything I've underlined in red here is equal to what I've underlined in red here, right? I'm just rewriting those two terms in a somewhat creative fashion. Now the plus c over a is still there. Okay? And that's all equal to 0. Now, what I do, all right, is I say, oh, okay, well, I'm going to rewrite this one more step as x plus b over 2a quantity squared, right? Are we over here? The camcorder, are we? Okay, cool. I just had a moment of like, uh-oh, wait a minute. And then this right here, well, let's rewrite that as minus b squared minus 4ac over 4a squared. So what I did there was I made a common denominator for a squared. See that? And I pulled out a minus. So if you multiply this by 4a over 4a, you get 4ac over a squared, 4a squared. But I'm pulling a minus out front like this, so I have to do that. So I'm just taking these two terms and rewriting them like so. Now, I make a very sneaky step. I rewrite that term as a square. How did we do that earlier last week? I had 6. I wanted to write it as a square. How did you do it? Rewrite 6 as the square of something. It's what squared?
Oh, the square root of 6.
The square root of 6 squared. So I use that same trick here. I rewrite this as the square root of that squared. Then what happens? What do I have after I do that? I have one of our favorite things, the difference of squares, right? And once I have the difference of squares, I can use the difference of squares formula to factor this. See, then this becomes x plus b over 2a minus the square root of b squared minus 4ac, right? By the way, let's simplify that a little bit. Can you tell me how to simplify this? The square root of b squared minus 4ac over 4a squared would be what? This would be the square root of b squared minus 4ac divided by the square root of 4a squared. What's the square root of 4a squared? 2a, right. Now, that's actually a lie, but it's a convenient one, so we'll go with it. Really, this should be the absolute value of 2a, but let me just put a plus or minus here because it depends on whether or not a is positive or negative, right? You may have forgot this. We'll talk more about it in a future lecture, but like the square root of a squared is equal to the absolute value of a. It's not just a. Like if a is minus 5, the square root of a squared is the square root of 25. The square root of 25 is 5. It's not minus 5. So if I take the square root of something squared, I really have to put absolute value. So to be fair, I have to put a plus or minus here, right? But so if you think through it, it doesn't really matter because you got a plus for one, you got a minus for the other. So we can just kind of ignore that plus minus and just put a 2a here. There's no loss of generality. If I was smarter, I would have just lied to you. Then you'd be less confused, right? Let's see here, x plus b over 2a. And we do plus the square root of b squared minus 4ac. Note to self, lie to next class. All right. No, I mean, I try to be honest with you guys. And so the difference of squares. So we do a plus a squared minus b squared, a minus big A plus big B, that pattern we saw last week, right? And this equals to 0. So this step right here is called completing the square. All right. What I'm doing right now, I would describe as solving by completing the square and factoring. Okay? There's another method, which is solving by completing the square and using the square root property. All right? We'll do both. Now what? The principle is this, right? If I have two quantities equal to 0, the only way they can be 0 is what? If either one or the other is 0, right? Can you have two numbers multiplied together to get 0 unless one of those numbers is 0? No, you have to have one of them as 0, right? So what does this give us? This either gives us, in this case, x equals to minus b over 2a plus the square root of b squared minus 4ac over 2a. Or in this case, we get x is equal to minus b over 2a minus the square root of b squared minus 4ac over 2a. Do you recognize what this is? What are we looking at? Oh yeah, they do have a common denominator. Let's clean it up. Let's write them nice and pretty like. So what we got here is that x is equal to minus b plus or minus the square root of b squared minus 4ac all divided by 2a. So that, my friends, is the quadratic formula, right? You can plug the numbers, the coefficients of your given quadratic equation, into the quadratic formula. It will tell you the solution. That solution could be what? It could be real and distinct. It could be real and repeated, or it could be complex, depending on what the values of a, b, and c are. Right? Because this thing inside the, b squared, if b squared minus 4ac is less than 0, that implies complex solution. Right? If b squared minus 4ac is greater than or equal to 0, that says that you have a real solution. A real solution. So let me show you completing the square and factoring as a means to solve an equation. And then I'm going to show you the square root property way of doing it, okay? Your homework really kind of tries to ask you to do both. So you're like, but the truth of the matter is I could just do the homework by looking at the problem I'm given, rewriting it in the standard form, and using the quadratic formula to find the answer. And then I can work backwards from that, right? That is true. You could do that. That's what I did. But I robbed myself of true understanding in this course when I took this course because I decided I don't like completing the square. It's not comfortable. I'm going to ignore it. That was a mistake. I finally came to terms with completing the square personally because I'm obstinate when I was in differential equations. At which point I was like, oh, this isn't hard. Why have I been making it hard all these years? So let's do it. What example was I on? Oh, 19. A lot of examples today. So here's one. X squared minus 10x minus 2. I'm going to factor this using completing the square. So here we go. I take half of 10, which is what? 5, right? So I square that. So what I'm going to be doing is I'm basically just going to be going through the steps over here. But for this specific example, it'll be easier to follow, right? So I take half of the 10, I get minus 5. I square that, right? Think through it. That would be adding 25. Is there a 25 here? There's not. So I have to subtract 25 to be fair. And I still have the 2 from the beginning. So what I've got here then is x minus 5 quantity squared minus 27. Right? But I can think of 27 as a square, right? 27 is really the square root of 27 squared, right? And so what do I got? I've got x minus 5 minus the square root of 27, x minus 5 plus the square root of 27. So I have factored the quadratic using completing the square, right? Now if I look at this equals to 0, right? What are the solutions? X equals to 5 plus the square root of 27, and x equals to 5 minus the square root of 27, right? Which we get tired of writing that, right? So what's an easier way to write all this? Plus or minus, yeah. So just to be lazy, we say x is equal to 5 plus or minus the square root of 27. There you go. Now you could rewrite 27, and your book does this sometimes with like multiple choice answers, so be aware of this. How could we rewrite square root of 27, like simplified. I don't talk too much about this because I don't think it's that interesting, but this is 3 times 9, right? Yeah. Square root of 3, square root of 9. Square root of 9 is 3. So this is the square root of 3 times 3, which I typically like to write 3 root 3, right? So an equivalent answer here would be 5 plus or minus 3 root 3.
Shouldn't you, you should then combine the like you can't add the 3 to 5 or subtract the 3 to 5.
No, they're these 5 with the root, I mean 3 with the square root, and we'd need a root 3 times the 5 in order to combine those. Yeah, they're
Okay.
apples and oranges. Yep.
For like -10, it's b over a.
Yeah.
Is 1.
Yeah, here a is 1s.
5. Why you divide?
How did I get 5? Well, 10 divided by 2 is 5.
Yeah, where does the 2 come from?
That 2?
Yeah.
It was there. It was there all along. It's this 2.
Oh, okay.
Yeah. Yep.
Why did you divide 10 by 2 again?
This is completing the square. So it's here. Here's another one. If I had x squared plus 4x plus, oh, I don't know, 7. Now I've got 4, so completing this square, I do, instead of x plus minus 5, this time I do half of 4 is 2, right? So x plus 2 squared. And then to be fair, I've just done what? If you FOIL out x plus 2 squared, that's like adding 4 in the constant term, right? So I must subtract 4 to be fair. That's 7. It didn't go anywhere. It's still there, so plus 7. And what do we got? We've got x plus 2 quantity squared plus 3. Now here's where it gets a little bit funny.
Can you explain why you subtract 4 one more time? I'm saying you in that part.
Because x plus 2 squared is x plus 2 times x plus 2, which is x squared plus 4x plus 4, right?
Yeah, and you, okay, you don't want
So I had,
you're just trying to get the x squared plus 4 plus.
yeah, I'm trying to group all of the variables into a square. So these two terms, I can trade for this minus that, right? So see, I started with this, and I traded it for that. That's always what I'm doing with completing the square. That's it. Now, if there's an a in front of the x squared, then it makes things uglier because it ends up putting fractions into the story a lot of times. But it's still the same story. You just have to basically suffer the division by a in the problem. All right, so 3 though, is 3 a square? Now here's where you got to be a little bit sneakier. We can write 3 as minus 3i squared. See, because minus I squared is equal to what? It's equal to 1. So 3 plus 3 is actually minus 3i squared, which you can look at this, right, as x plus 2 quantity squared minus I root 3 squared. Again, it's the difference of squares, so we can factor it. This is a prime polynomial,
Why would you add the I if you didn't need it then?
but we do need it to factor it. And the reason we want to factor it is if you want to solve a quadratic equation, the first line of defense we have is just factor it. Once we factored it, we set it equal to 0, and then that means either one of the factors or the other has to be 0, right? So in this case, for this to be 0 or that to be 0, if we set this equal to 0, that tells me my solutions are x equals 2, minus 2, plus or minus I root 3. This is a prime polynomial. That means it has no real solutions, right? Because the factorization of it necessarily, that sounds wrong. You can't avoid using complex numbers to factor this. You just have to.
But how do you know when you're not using a complex number?
When b squared minus 4ac is less than 0, that corresponds to there being a complex.
Test it every single time that you do it.
I would argue no. I would argue that completing the square is faster than checking that. If I complete the square, when I'm done, after I do the arithmetic and the dust settles, if what I have left here is minus a real number, it factors into a pair of reals. If it, on the other hand, simplifies and I have plus a real number here, it's the complex case. Them's your choices. Or it could be 0, in which case you already factored it.
How would it look if you were to not put the I in? How far would you go?
I couldn't do it without putting the I in. Like, the I has to be there. If it's there, it's there. Like, I can't rewrite 3 as minus the square root of something squared without using I.
Okay.
You can't do it.
Okay, I get what you're saying.
Let me work a way easier example here before I say more about completing the square. How about this one? What if you wanted to solve x squared plus 3x plus 2 equal to 0? How would you do this one? Do we need completing the square for this? Do we need the quadratic formula for this? I would argue no. This one, we just need to factor. Plain and simple. This is x plus 1 times x plus 2 equal to 0. Right? What are the solutions? Either x plus 1 is 0 or x plus 2 is 0. Right? So we either need x plus 1 equals to 0 or x plus 2 equals to 0. That's how you can solve that equation. So the answers are either what? Minus 1 or minus 2. So what technique should you use to solve a quadratic equation? It depends on the problem, right? I would say if it's got ugly decimal numbers in it, use the quadratic formula. That's definitely the way to go. But if it's got nice whole numbers and the leading coefficient is 1, like my example 19 or 20, completing the square is a pretty good way to do it. Now the other method is the square root property, right? So I'll finish class with one of the square root properties, unless there's a question, in which case I'll just put it off till next time. Question? Here, let me show you how example 20 looks like with the square root property version. So example 20, square root property argument. So we start out the same way. We complete the square. All right. So same thing. But a lot of you are going to like this more. But then what we do is we isolate the square. Isolate the square. So if I had what? I had a 3 here, right? So if I put the 3 to the other side, I get minus 3, right? Now, to solve for x, I do what? I take the square root of both sides, right? To be fair, remember, square root allows plus or minus in this way. So this gives us x plus 2 equals to plus or minus the square root of minus 3, which gives me x is equal to minus 2 plus or minus I root 3. Now, as I was telling you all last week, math is not postmodern. There is a single truth that we all must believe in and unite around. In this case, the truth is that x is equal to minus 2 plus or minus I root 3 for this quadratic equation. This is the square root property way. So isolate the square, take the square root of both sides. Which do you like better? The factoring way or this way? I kind of like this way more if I'm doing it this way. So listen, guess what we're doing Wednesday? This. So I just wanted to get us started today. So anyway, thanks guys. You have a good weekend. Was it exciting?
Yeah.
Anything interesting happen that you can tell me about?